First, I would like to thank the organizer, and it's good to see Kang and Rosie and others in this conference. I will start with a comment Kang made at the end of the talk about useless and useful. I don't know, since when we ask about useless and useful algebraist? I mean, for me, and I think the rest of us, we do things for, and it never crossed my mind if this is useful. Anyway, that's a long story to talk about, and so I will start with my talk.
Well, I have a comment. I'm getting old and I feel like I'm useless.
No, I didn't mean that, Kang. You know what I mean. I, uh, I mean, in fact, for me, I love useless. We have enough of the useful. Let's stick with the useless for now. Yeah, I don't think we need anything more useful. That's my opinion, anyway. Uh, okay. Uh, let's see how I. Okay. I'm gonna start with the classical question, just like the previous speaker. This is sound like maybe you will expect that somebody answered this question a long time ago, when the polynomial ring over a commutative ring R is a principal ideal ring. That seems like, wow, what are you asking about? I mean, this should be known. I'm not sure if this is known to you, but I get to know the answer to this question recently, maybe 4 months ago. Uh, the speaker, I mean, the author of this paper, he gave a talk in one of the conferences, and I was shocked that such question was not answered 50 or 70 years ago. Uh, I mean, the answer to this question appeared in a paper in 2017 or 2018 to this question. And look at the answer. The polynomial ring over R is a principal ideal ring if and only if R is ring isomorphic to a finite product of fields. Wow. I mean, it cannot be simpler than that. The paper is about 6 or 7 pages, and of course, rely on other. It's not like, like one piece by itself. I think he quoted many work that lead the authors to the answer. And for me, whenever I see this result, I get excited. Uh, Maybe some of you know it, but I never seen this before. And the classification is very simple, and that will answer, like many of the questions. Like all of us know that polynomial ring over a field is a principal ideal ring. Well, this is nothing, just to stare at the theorem and let n to be 1. You're done. All of us know polynomial ring with two variables over a field like is not a principal ideal, because you think of fx comma y as your ring R to be f of x, and you add to it y. and definitely f of x is not a field. And many things like x over polynomial ring over integral domain, uh, where the integral domain is not a field, then this is not a principal ideal. Like Zx, all of us learned that Zx is not a principal ideal ring. You don't have to do much just by staring at the theorem. Anyway, I thought I shared. Kang, you can interrupt me. I'm not, Do you know this result before?
No, not a few seconds ago.
I cannot hear you.
Not a few seconds ago.
Oh, okay. So this is kind of a very nice result. I thought I shared that with you.
Dan Anderson or Robert Gilmer might have solved this problem, but somehow it never be.
I don't know, your voice is not clear to me.
Sorry, I didn't use the microphone. This is a very surprising result, and I think Dan Anderson or Robert Gilmer or Bill Heinzer might have been interested in this kind of problem, and I wonder why they couldn't think about this.
Yeah, well, that's the thing. That's why I mention it here. And I almost mention it in every, because if this is known, I mean, at least we should know about this. Even I never seen this result before, and it's published anyway. Uh, but sometime the referee, I mean, like if this paper came to me, and if it's already known, most likely I will accept the paper because I don't know this result before. So I just want to make sure. Okay, anyway, thank you.
But isn't it anyway related to some rings, such rings as general ZPI rings
Yeah,
or
I
something?
think exactly. In the proof, they use that. I mean, they use that thing and they use other things to prove this result. In fact, this become like maybe after relying on many things done, it will be like short proof. Uh, but I mean, I have not seen it in this form. This,
Then I have a natural question because you allowed me to interrupt you.
yes, sure.
Here's a question. What happens if you consider a power series ring? When is all double bracket X a principal idea ring? We can naturally ask a similar question.
Yes, I agree with you, and that's your job now. You are the expert on power series.
No,
Uh,
I've never thought about it. Certainly, I'm getting interested in that question over power series ring.
yeah, I think that will be also kind of, if we have an answer or if you can give us an answer, that will be kind of, will be interesting for sure.
Well, like you mentioned, if R is a direct system of finite many fields, then definitely the power series ring is a principal idea ring, right?
Yes, I think, yeah, I mean,
One direction is clear, right?
one direction is clear, as you said, because not because I know it, because I trust what you said, Kang. I don't see it really, but you said it's clear, so it is clear. No, I mean, I'm not trying to be silly, but I never thought about the power series, what's gonna happen. My goal here, just to give you, uh, you know, I share this result with you, and it seems I excite some of you. At least Kang get
Uh,
excited about this. Okay, I go back to my talk now. Uh, okay, so two absorbing ideal. This is started in 2007. I defined this term, and let me remind you with the definition. A proper ideal is called two absorbing if whenever A, B, C in I, oh, this is not for some A, B, C in R, not in I. Yeah, that's all ideals are too absorbing. Yeah, here that's crucial. A, B, C in R, not in I. Then A, B in I, or B, C in I, or A, C in I. And over the 15 years or so, there has been considerable attention to two absorbing ideals and many generalization. I can mention some names, like here is a paper appeared in Communication in Algebra in 2020 on factorization inside factorization ideals into two absorbing. Um and here is some more references. I mentioned them at the beginning, and more references. There is one absorbing primary, that's the recent one, and there are many. Okay, a more general concept that two absorbing is in absorbing. What does in absorbing mean? Whenever you choose n plus one element in R, and the product of the n plus one element in I, then there are n of the AIs whose product is in I. So like when you tell me for absorbing ideal, what I understand, whenever I have five elements in R, and the multiplication of these five elements in I, then there are four of the five element whose product is in I. Okay, of course, this notation radical, what I mean with the radical of an ideal, all of us know that. Okay, then we have strongly in absorbing. Strongly in absorbing is replacing the element by ideals. Well, here's the definition. Whenever you have n plus 1 ideals of R, and the product of these n plus 1 ideal is a subset of I, then the product of some n of the i's is contained in I. So to follow I mean, and this is why maybe I should mention that earlier. You can think of two absorbing ideal as the generalization of a prime ideal, because the prime ideal, whenever you have a product of two in I, then one of them is in I. So two absorbing, whenever you have a product of a three in I, then a product of two is in I, and so on. And we know that in case of how you have a prime ideal, then whenever you have a product of two ideals in I, then one of them has to be in I. So this is, like the same thing. We replace the elements by ideals in the definition, and in this case, we call it strongly in-absorbing. And we need this name because till this minute, I mean, I know that we don't have a complete answer to the question. Which question you're gonna tell me is in absorbing imply strongly n-absorbing? Because it's clearly strongly n-absorbing, sorry, will imply n-absorbing. But the question will n-absorbing imply strongly? Okay, there are in some cases yes, and our feeling that the answer should be yes, but we don't have a proof and we don't have a counter example. Okay, here is some conjectures myself and David Anderson made in 2011, that if I is n absorbing ideal of a commutative ring, then if you take the radical ideal to the power n, then it is a subset of I. This conjecture, it has like two independent proof. So the conjecture one is done. The answer is yes. And there are two different proof for this result. Conjecture two, if I is an absorbing of a commutative ring R, then I is a strongly n absorbing ideal. This is what I just told you. In some cases, yes, but we don't have a complete answer in general. Okay? And conjecture three, if I is n absorbing ideal of a commutative ring R, then the Ix is n absorbing ideal of Rx. Okay? This is also no answer. I mean, in some cases, yes, but we don't have a complete answer to conjecture 2 and 3. Conjecture 1 completely answered. In fact, there are two authors in two different papers and independent work. They gave a proof of the conjecture 1. Okay, so let's move on. This is what I told you. That's the name of the authors who prove conjecture 1. That appeared in 2020 Journal of Commutative Algebra. That is run by James Cokendale. Maybe I think all of you familiar with it. Appeared in 2020, and the same conjecture the proof appeared in 2018. And you're gonna ask me, is there a gap? I think the paper for Chow and Walker appeared, get accepted during 2000 something, but appeared in publication in 2020. In fact, when you look at the two proof, they are completely different proof. Okay. Okay, for conjecture number 3, if I is n absorbing ideal of a commutative ring, then Ix is an n absorbing ideal of the polynomial ring. I gave a positive answer to this question when n equal 2. And myself and Anderson, we gave also a positive answer when R is a proofer domain. If R is a proofer domain, then this conjecture is okay. Then in 2017, Laragi, I'm not sure if I pronounce his name correctly. He gave many results and many cases. One of them, he proved that conjecture 2 and 3 are valid for any arithmetical ring. And of course, proof or domain is an arithmetical ring. So our result becomes a special case of his result because he proved that conjecture 2 and 3 are valid for any arithmetical ring. And also he gave this kind of interesting connection. If you can prove that conjecture 3 is correct, then conjecture 2 is correct. So conjecture 3 imply conjecture 2. Conjecture 3 has to do whether IX is n-absorbing. When I is n-absorbing ideal of a ring R. If you can prove, then IX has to be n-absorbing ideal of Rx, then this will imply conjecture 2, which is n-absorbing imply strongly n-absorbing. Okay. You know the definition of U-ring, that an ideal contained in a finite union of ideals, then it must be contained in one of these ideals. Okay, this is U-ring. In 2017, Hizam, Samak, maybe Kang know one of the authors here. In 2017, they prove conjecture. Here is what they prove. If R is a U-ring, then conjecture 2 hold. Meaning, what conjecture 2? Conjecture 2, n-absorbing implies strongly n-absorbing. Remember, n-absorbing is the definition in terms of element. Strongly n-absorbing is replacing the elements in the original definition by ideals. Okay? All right. And here I remind you what we mean with pseudo-valuation domain. There are many. I mean, this is not the original definition, but I think the best way to think of pseudo-valuation domain with exactly one maximal ideal, and M is a value, and the over rings M colon M is a valuation domain. And then I remind you with what we mean with the content of a polynomial. Like if you have a polynomial in Rx, so what is CF is the ideal generated by the coefficient of the polynomial. And a Gaussian ring mean the content of F times J is the same as the content of the first times the second. So we have prove this result. Hizam, if R is a U-ring, then conjecture 3 hold. Sorry, if R is U-ring and a Gaussian ring, then conjecture 3 is correct. What conjecture 3? That if I is an absorbing ideal of a ring R, then IX is an absorbing ideal of RX. And if R is a pseudo-valuation domain with maximal ideal I, and the radical of I is not M, then I is in absorbing ideal of R if and only if IX is in absorbing ideal of RX. So this is kind of a connection, but if your domain is pseudo-valuation domain, then conjecture 3 is correct as long as the radical of I is not M. In fact, you're going to see in a minute that this is not needed, this condition, the radical of I not equal to M. The conjecture is still true. Uh, okay. All right. And then if you combine what Lalarge said, that conjecture 3 imply conjecture 2, then quickly you conclude what I have here. I mean, this is by staring at the previous result. Quickly you conclude that if R is a pseudo-valuation domain, and as I told you, this is not needed, the radical of I not equal M, then I is in absorbing if and only if IX is in absorbing ideal of the polynomial ring if and only if I is strongly in absorbing. Okay. In 2001, myself and David Dobbs, we defined locally divided rings. And what is here is the definition of divided ring, that if you have a prime ideal, call it Q. And maybe some of you maybe wonder, why did I call it Q? Natural thing is to call it P. But you know, my P and B, they look the same, they sound the same. So I decided to avoid pronouncing the letter P, so I decided to choose Q. So that's the reason why I'm not using the letter P, because I don't know, I cannot pronounce this letter. It always sounds like B. So I selected a Q. Uh, and that's the definition of divided ring. Okay, and locally divided, let's see, yeah, it's called locally divided if R localized at P is a divided ring for every prime ideal, I change it to P again, of R. Let's see if R localized at Q is a divided ring for every prime ideal Q of R. All right. Recently in this paper 2022, Chow, he proved this result. I cannot get this bar away. Okay. If R is locally divided, I don't know what, yeah. If R is a locally divided ring, then conjecture 2 and 3 hold. Okay? And definitely pseudo-valuation domain are locally divided rings. So that means he gave a more general result. If your ring is locally divided ring, then these two conjectures are the same. How much time left for me, Kang?
Minus a few minutes.
Okay, I try to finish up. Uh, Here is definition what we mean with AF dimension of a ring R is the smallest positive integer n such that each proper ideal of R can be written as a finite product of n absorbing ideal of R. So this is kind of factorization thing. The AF dimension is the smallest positive integer n, where every ideal can be written as a finite product of n absorbing ideal. And here is an example. If you take these, an integer square free, and you choose 4 is a factor of d minus 1, and 8 is a factor of d minus 5, then this ring is FAF ring, and AF dimension is 2. So that means every ideal in this ring R can be written, every ideal, as a product of two absorbing ideals. Okay. Yeah, they prove in this paper 2022, Chow, if R is a FAF ring, then conjecture 2 and 3 is hold. Remember what FAF ring mean? Mean such smallest integer n exists. That means there exists an integer n where every ideal is a product of some absorbing ideal. Maybe some of you, if you are interested, this is a recent paper, maybe you can look it up, at Chow. So he made improvement on these two conjectures. And I think I stopped. There is no time to talk about 2AB ring and so on. I will stop here. If you are interested, in fact, here is it. I have to say something about that. My contribution in all this talk is nothing except, the definition of absorbing ideal. All this work done by others. But when okay, look at this corollary. Look at A and B and C. A and B and C, they are they appeared in a paper in communication of algebra. I only added number D to it. Why? Because in as I told you 4 months ago, I got to know the result that Rx is a principal ideal ring if and only if R is a finite direct product of field. So I only added D to the condition, to the statement ABC. I added D, which is by just by knowing, not because here C is a finite direct product of field. Then I said, oh, this remind me with something I just learned recently. That means Rx has to be a principal ideal ring. That's all I have. And thank you. And I'm sorry, I don't know what happened. Instead of subtracting 3 hours, it seems I added 3 hours. And thank you very much.